Good evening, everyone, and welcome to this part two of the Exoplanets course. We had three sessions last week, and this is the second week of the course. And today we have with us Dr. Jayesh Goyal. So, Dr. Jayesh Goyal is Assistant Professor at National Institute of Education and Research, which is NISER, Bhubaneshwar. And today he is going to talk about habitability of planets, about the exoplanets, and how is the atmosphere out there, and so on. Over to you, Dr. Goyal.
Thank you, Prachi, for that introduction. So everyone is able to hear me clearly, I guess. So Prachi and the Gayatri can confirm.
Yes, we can hear you, and the video is very clear.
Okay, and the slide is also the full screen view?
Yes, now it is, yes.
Okay, perfect. Yeah. Thank you very much for that. And thanks, Prachi, for the introduction. So hello, everyone. Welcome to this Exoplanet course. So I already Prachi mentioned about me. So I am Jayesh Goyal. So I am Assistant Professor at School of Earth and Planetary Sciences in NISER, Bhubaneshwar. So this is in Odisha state. So I'll just give a brief introduction. So I did my PhD at the University of Exeter in the UK, studying exoplanet atmospheres, and further continued the same during my postdoc at Cornell. And then I joined NISER in 2021 June. So I have always been fascinated about exoplanets. I should not say always. When I got to first know about them from that time. Before that, I was mainly interested in planets in the solar system, Venus and Mars, because I was aware of them. Once I started to read, and I got to know that we have started to find planets around other stars. That made me very excited. Like how might these planets be like? What will be on them? All these questions started coming in my mind, and that is when I thought of going in that field. And I was lucky that I got an opportunity to work in that field, and I'm currently doing the same. Okay, so today in this class, I will basically cover exoplanet atmospheric characterization and observables, and talk a bit about their interiors, how the connection between. Okay, so we'll start our this class now. Okay, so in the previous classes, which Dr. Ajit and Dr. Ravi might have covered, so there I saw in the the timetable that they covered the stellar spectroscopy, stellar spectrum, that part, and Ravi covered the techniques to detect exoplanets. And so I'll build on that and move ahead. Just give you the brief primer of what has been, what you might have learned before. Okay, so in what Ravi would have talked about is the different methods by which exoplanets have been detected. So that that helps us in answering what are the different types of exoplanets out there. Okay, so these exoplanets have been detected using different kind of surveys. WASP survey, that is wide angle survey for planets, HARPS and Kepler. These are the different radial velocity transit and direct imaging, different kinds of surveys detect these planets, they find them. Okay, so using and until now, after finding, means because of these detections, we have reached more than 5,000 number. So this this slide is very interesting. You might hear a background noise also. So this is basically showing you, and this is quite old. You can see the number. It's from 2011-12. So this is basically this different exoplanet systems that we have detected at that time. All of them, there means to scale it is being shown, to how close they are from their host stars. Our solar system is shown. So the main takeaway from this thing should be like how the number of exoplanets that you've detected is just very large, and there is so much variety out there. That is the main thing you should take away from this, the variety out there. And you will see one more thing here, where you'll notice one more thing, that our solar system is quite big in terms of its span. Like you have the sun, then you have planets that are spanning very far away. But the exoplanet systems that we have detected, they are very close bounded. Okay, so any guesses on why that is the case? Like why the systems that we have detected are very close bounding, while the solar system is very large? Anyone wants to answer that?
Is it just an observational constraint?
Yeah, so someone said something. Sakshi, yes.
Yes. Is it just an observational constraint, considering if they are very far, we cannot detect it, and the close
Correct.
by planets we are detecting?
Exactly. That's our observational bias. So
Yeah, yeah.
basically, it is the bias in our observations because the planets that are closer into their host star, they will be easier to detect. And why is that? I'll come to that in a minute. Because if you use, Ravi would have covered that. If you're using a transit technique, then the planet is closer. So it takes less time to go around its host star. So you can detect planets easily. Because to confirm a transiting exoplanet, you should at least detect 3 transits. So if it is closer, if it takes just like 10 days or 5 days to complete this orbit, in like total 15 days, you can just confirm the planet. So it is this bias in our observations that is causing, that is the reason why I have detected many planets that are closing to their host star compared to what we have in our solar system. So it's not like that is common, but it's just the bias in our observation, which is the important thing to understand. Okay. Sorry. There was an in the chat, someone answered that the planet migrates in. So that's a good point. You can say that that happens, but that is not the case in the statistic that we are seeing. Because in this case, what you're seeing the planet, this is the real observation. So in this case, we don't know. We don't have that information whether they would have migrated or not. So that is why we can't come to that conclusion from by looking at this image of this animation. Okay. So the exoplanet population that we have, as I said, like has currently reached more than 5,000. Okay, and what you are seeing here is on the x-axis, we are plotting the orbital period, like how long do they take to orbit their host star, and the y-axis size relative to that that of the Earth. So here 1 corresponds to the size that of the Earth. Okay, so you can see the variety that we have detected. It's just astonishing. We have so many planets out there. Some have size that of the Earth, but are very close to their host star because the orbital period is 1 or 10 days. You can see many of the planets. Our Earth lies here because our orbital period is 365 days. Okay, so that is very fast. So we don't have exact like that 365-day orbit and size that same of the Earth. We don't have any planet like that, but we have planets similar size that of the Earth, but very close into their host stars. We have planets that are very far away but bigger size. There are planets which are very close in and bigger size. So there is so much variety that means our minds cannot comprehend. There are planets same size as Jupiter, planets bigger than Jupiter, smaller than Jupiter, size of Neptune. Then there's this full range which does not exist in our solar system. We do not have any planets that are like 10 times that of the size of the Earth. So they are termed as super Earth planets. So looking at this variety, the first thing that at least comes in my mind, and I guess you, is like, if there is so much variety, there must be so much variety in the types of environment these planets might have. Like they might have different kinds of atmosphere, different interiors, and that could, there is a possibility that they might have different kinds of life forms also if they are habitable. So all these questions come in our mind when we look at this statistic of planet. So as I said, like we have detected more than 5,000 exoplanets. So the first questions that we try thinking once we look at this, we have 5,000 exoplanets. So what do we do now? So the first question is, does it have an atmosphere? Now, atmosphere is very important. I'll come in a minute. Why is that? And then do they have any clouds or haze? What is their atmospheric composition? And one of the important questions that every one of us is interested in, like, are there any aliens? Means, are there any intelligent civilizations living on these planets? So all these questions come in our, but all these questions are connected. We need to answer them step by step. And so we need to constrain, first of all, we have to answer, does it have an atmosphere or not? What is atmospheric composition? Is it habitable? Does it have, all these questions have to be answered to come to the possibility of, are there any aliens or not? Or to answer that question. So before going into that, answering those questions, we need to understand one thing, like exoplanets are really, really far away. They are very, very far away. So when I was saying that we have detected exoplanets, we should study their atmosphere and we should try to understand, does it have an atmosphere? So like imagine you are 20 years behind when you detected your first exoplanet. So the first question that will come in your mind is, can we really study their atmosphere? They are far away. So why am I asking this is because these distances are very far away. Our mind cannot comprehend how far these distances are. So that's why I have added this small quiz for all of you. So, so to calculate how far away they are. So this is the time I am asking you to calculate. So all of you can take your notebook and pen. This is very simple. I think you should be able to calculate it quite easily, and you can send your answers on chat. Okay. So the time it will take with the fastest man-made object. So the fastest man-made object currently is the New Horizons spacecraft, which actually went to the Pluto, is near the Pluto actually. And if we take the same spacecraft and we send it to the nearest exoplanet, which is Proxima Centauri B. So how long will it take? So I'm just asking to the closest to batch value means approximately how many years or how many months or seconds or whatever the answer is, do you think it will take? I will suggest give your answer in months or years. It will take to reach Proxima Centauri B using this fastest spacecraft. And for that, I'm giving you the velocity of New Horizons spacecraft, 16.26 kilometers per second, and the distance is 4.25 light years. So how about like in 5 minutes, you come up, you solve this and send your answers on chat. And don't worry if the answer is wrong or something. Here we have to learn. So there is no one is judging you. So feel free to send whatever you get. Okay, so I have someone answering it in seconds. Okay, Shri Krishna, can you convert that into years? How much is that? Sakshi Gupta is sending me in. Okay. Okay, so Anushka is sending it in 80,000 years. Okay, so that is close. 78,000. So exactly. So we have started getting answers. So it's close to somewhere 78,000 years. Now imagine that number, 78,000 years. Our lifespan is 100 years. So just to reach our nearest exoplanet, that is the nearest exoplanet, it will take us 70,000 years to reach there. So imagine how far away these distances are. And that can tell you how difficult it is. And someone has given like 100 decimals from somewhere. So that is Bruno. Thanks for that. So imagine thinking of going on this experiment. These are very, very far away. So studying them is actually very, very difficult. Okay, so that is why. So my point here to convey is that when we want to study their atmosphere, it's very challenging because these planets are very far away, and to get the radiation from them that is representative of their atmosphere is very challenging. Okay, so with that note, we'll move ahead. Okay, so the first exoplanet was detected in 1995 around a sun-like star. The first exoplanet was detected around a pulsar in 1992. So these were the initial detections. And then for the first time, an atmosphere of the exoplanet was studied in 2002. So just like almost 20 years before. So this is that paper that is telling you detection of an extrasolar planet atmosphere. You can see the title itself says that, the detection of an atmosphere. So this was the first time we got to understand that these exoplanets have atmosphere and we can study them. And this was using like the Hubble Space Telescope. Okay, so basically they studied planet HD 209458 in the region of the sodium resonance doublet at 589.3 nanometer. So what does this mean? All these things. So you don't have to worry if you don't understand this, because I'm going to go into the details of all this. So only thing you should understand is this was the first detection. Okay, so once we got the first detection of exoplanet atmosphere, everyone started thinking, what next? What questions we can answer? So the people started thinking about the big questions. What is the diversity in exoplanetary atmosphere? What are the different exoplanets that exist? How do exoplanets and their atmospheres form and evolve? How they form and evolve? Is our solar system and Earth unique? How did we get here? Are we alone in this universe? All these questions, because once you have an atmosphere, that raises a lot of possibility. Because if you think of the solar system, the planets which don't have an atmosphere, there is means almost very little chance to have a life on the surface. Of course, you can come and say that Europa might have subsurface oceans and life in it, but we don't know that for sure. But if you have an atmosphere, the surface life that we have on the Earth, similar to that, the Earth is possible. And the other is the presence of atmosphere can have a lot of variety in the chemical composition, the winds and all that, like we have in a solar system, Mars, Venus, Earth, Jupiter, Saturn, different colors, all those things come into picture. So when we start to understand about the planet's atmosphere. Okay, and the atmosphere also plays a very important role for life. And you can see how it plays an important role. The Earth's radius is 6,400 kilometers. Atmosphere is just like the most dense part of it is just 100 kilometers, and this 100 kilometers makes life possible on Earth. Because if we do without greenhouse effect, if you calculate the temperature of Earth just based on the distance from the host star, which is the Sun, we get around 255 Kelvin, which is around minus sorry, it should be minus 18 degrees Celsius. Okay, so minus 18 degrees Celsius, and with greenhouse effect, that is basically 288 Kelvin. So that is 15 degrees Celsius. Okay, so just this difference of how much it is, that 18 plus 15, 33 degrees Celsius is causing for the life to exist. Okay, so this is minus 18. If the atmosphere of the Earth would not have been there, just because of the presence of greenhouse effect, we have this cozy environment where the life can evolve and flourish. And every day we experience that. That we have this nice temperature that makes life possible on. So this is what atmosphere is doing for the presence of life on. Okay, and why atmosphere is important for habitability? We can learn the lesson from our own solar system. So here we have two very twins. They are twin planets, Earth and Venus. They almost have similar size, but if you look at their temperatures, now the equilibrium temperature of Earth is 255 Kelvin, but the actual surface temperature is 288 Kelvin. While for the Venus, the equilibrium temperature is 260 Kelvin, but the actual surface temperature is 700 Kelvin. So that's a big difference. So the actual surface temperature is governed by what the atmosphere is made up of, its atmospheric composition, the ready to transfer, the energy balance. So this 288 Kelvin makes life possible on Earth, but 700 Kelvin on Venus makes life like hellish on Venus. Like there is no way life can flourish there. On Venus, you have hydrochloric acid, sulfuric acid rains. The temperature is so high, which makes life impossible to form on Venus. So this is the lesson that we learn from our old solar system when we try to understand why atmosphere is important for habitability. Okay, so if anyone has any questions, feel free to. So, okay, I have one question in the chat regarding understanding the possibility of by understanding the atmosphere. Does the atmosphere have to be similar to that of our does the atmosphere of those have to be similar to that of our planet Earth? It can also be possible that atmosphere there might be appropriate for us, but can be actually appropriate for life not much similar to that on planet Earth. So will understanding atmosphere be enough for understanding the possibility of habitability? Okay, so you should not be worried about it. This is not a stupid question. Actually, so that's a good question. So basically what Arpita is asking is, currently means does the atmosphere of this have to be similar to that of planet Earth? So for the answer is that no, it need not be similar. It can be something else, still life can exist. Okay, because and the other part of the question is, it can also be possible that the atmosphere that might be appropriate for, but can be actually appropriate for life not much similar to that of the planet. So if there is a different kind of life, then it can. So yes, that is also possible. So so that's a good point that you're raising. So the thing that we have to understand here is currently we don't know any other life forms. We have not detected any, we don't know how they function. So all our current understanding or current that we are moving forward in terms of understanding the habitability, we take Earth as a benchmark. So we use Earth as a benchmark and use that to determine the habitability. So it is correct to say that means there might be different life forms, different kinds of atmosphere, they might need different kinds of, but we don't know that. So it is like instead of, and I won't say, some people are working in that research area also. Like they're trying to determine how will the different life forms evolve, how they can form. But currently we are starting, we are mainly focusing on what we know, because we don't even have the information of what we know. Because we haven't found planets which are very similar to that of the Earth. We haven't been able to study the atmospheres of Earth-like planets. So all these questions are unanswered. So we are like, before we try to solve complex problems, we are trying to solve simple problems. In that sense, I can say that. Then there are two more questions. One is that, is there any effect of aerosol in atmosphere to make it habitable? Yes, it can have an effect because aerosols are part of the planet's atmosphere. So aerosol can help in heating or cooling the atmosphere depending on their properties, like what kind of aerosols are they. Like in the Earth's atmosphere, we have some aerosols like black carbon, which are quite absorbing in nature, while some are very reflective in nature, like sea salt or other kind of aerosol. So depending on what is the property of the aerosol, it can have a effect on the habitability of the planet. Yes. So, and there is one more fundamental question. What does equilibrium temperature mean? So, okay, so that's a good question. So the equilibrium temperature, basically the definition of this is the temperature that is measured just considering the distance from the host star. Okay, so in that case, the atmosphere part is not taken into effect. So what we do is we basically just take the amount of radiation that is for the Earth, the amount of radiation that come at the top of the Earth's atmosphere, and how much of that is reflected. That's it. We don't consider the greenhouse effect that is happening in the Earth's atmosphere. So it does not take into account any radiation is trapped by the atmosphere. That's why it comes out to be colder. Okay, so it's just based on the distance from the host star. Okay, and the other question is, other than temperature, do you think magnetic field plays a major role to habitability on Earth and Mars? Yes, definitely. I would say magnetic field also plays a role, because that determines if the atmosphere will stay or not. Because if the magnetic field is there, it can protect your atmosphere from being stripped off by the stellar, the stellar photons or stellar flares that form, or solar flares in our case. So this magnetic field of the Earth protects it. But if you don't have magnetic field, there are chances that your slowly your atmosphere might just get stripped away. Okay, so and the other question is, so how do we exactly define life form? So here, to be frank, I would say I don't know, because here the answer, there are innumerable answers to this. Okay, because in a sense, currently the life is defined in three ways for our understanding on Earth: that it should have some solvent to mediate the reactions, which is water, then some kind of biomass, which is carbon, and it has energy. So so the question that you are asking, how do we exactly define life forms? It's not that easy answer. Means I don't think anyone in the world would answer it accurately, because what life is, it's still a big question. Okay, so I won't attempt to answer that in this talk. Okay, so there are many questions I can see that are coming. So can I try to answer this at the end of my talk? Because otherwise it will just go on and I won't be able to go ahead. Will that be all right? Okay, so there are just two questions. I'll just answer those and then we'll move ahead. The life that we know is evolved from the Earth's atmosphere. The basic blocks which form life originated to the Earth's atmosphere. So for planet, life would change, right? So I won't say that is true. Like Earth's atmosphere has played a role in that, in protecting the life, but the life might have evolved in the Earth's ocean or even in the subsurface. So we don't know that. So to answer your question, the definition of life would change. So I can't say, of course, it can change if you're looking for different life forms, but maybe if you have another planet which has similar like atmosphere that of the Earth, it can have similar life form, but it also can have different life forms. So there is no like definite answer to that. And then, can Venus create, last question that I see in the chat, can Venus create substantial ionosphere from its own thick atmosphere to stop losing it to the solar wind? I am not sure, because from its own thick atmosphere. Okay, because generally the magnetosphere is produced due to the in the planet's interior, because of the mantle convection and the core convection. That are the main reasons that produce the magnetic field. So for Venus, can its atmosphere, thick atmosphere, produce? I'm not sure. I'm not sure about that. Okay, so moving ahead, so here now we have noticed like why atmosphere is important for habitability, and we have learned these lessons from a solar system. So that gives us enough motivation to study the atmosphere of the planet. Okay, so and while studying this, I told you about the big questions. But these big questions have many small detailed questions inbuilt in it. Like which molecular species are present in the exoplanet atmosphere? What are their abundances? What is the temperature distribution on these exoplanets? What kind of chemistry dominates? What thermochemical processes dominate the atmosphere? Do these planets have thermal inversions? If yes, what species is causing them? Are there any trends? Can we have classification like stars? What is their atmospheric metallicity? Metallicity is generally the term used for all the elements heavier than hydrogen and helium. What is their carbon to oxygen ratio? Are they cloudy and hazy? All these detailed questions come into picture, because if you want to answer big questions, first you need to answer these detailed questions, because then only you will be able to answer those big questions. So these are some of the detailed question I was that can be answered by studying the planet's atmosphere. So how do we answer these questions? Okay. So Ravi would have covered one of the techniques to detect planets, which is the transit method. Okay, so this transit method has been one of the most successful techniques to detect exoplanets. So what we do with this, he might have covered the details. I'll just give a brief explanation. Like when the planet goes in front of the star, there's a dip in the brightness. And this dip in the brightness is what we measure. And that is how you detect the exoplanet. So the smaller the exoplanet, smaller is the dip, bigger the exoplanet, bigger is the dip. And simply this is how you detect the exoplanet. So out of 5,000 exoplanets, more than 70% have been detected using this technique. So this technique is very, very effective in detecting exoplanets. Okay. So that being said, so now we have 5,000 of those exoplanets. Now, can we study the atmosphere of all of them? Like ideally we would like to, but practically, can we study their the atmospheres of all of them? So the answer is it is very challenging to study the atmosphere of all of them. As we go ahead, you will realize why. So in that case, what we have to do, we have to choose which targets, which planets are the best for atmospheric studies. Okay, the one case is some planets you can't study the atmosphere because their atmosphere might not be, first of all, it might not have an atmosphere. Second, the atmosphere might be small. Then as I will come forward, I'll mention which properties you should actually measure, like determine to say if the planet's atmosphere is feasible for study. So these feasibility studies are actually done, because if you want to study the planet's atmosphere, you need to know if it is capable of doing that. A particular telescope will be capable of doing that or not. In general, the larger the atmosphere, the better it is for atmospheric studies. Okay, and why is that? I'll tell you. Okay, so there is this one terminology that we generally use. It's called in atmospheric science, it's called the scale height. So this scale height determines the extent of the planet atmosphere, like how big the planet atmosphere can be. Okay, and this is computed using this something called so H is the atmospheric scale height, and it depends on 4 parameters, out of which this one is actually a constant. So KT by mu G, where K is the Boltzmann constant, T is the planetary temperature, mu is the atmospheric mean molecular weight, and G is the planet's gravity. Okay, so using this, we can compute how big the planet atmosphere can be. It determines the extent of the planet's atmosphere, and I'll show you how. Okay, so there is. Okay, so there is one small question regarding, so you can ask technical questions if you have. Okay, so do you have a lower limit of 100 or to study that, because Earth is 100 kilometers, else what is the lower limit? Okay, so in that plot, I mentioned 100 kilometers because so it is not a lower limit in a sense. Okay, so there is no lower limit in a sense. In that, I am just stating a fact that most of the Earth's atmosphere is contained within the 100 kilometers. So just I want to give you a sense of how big the planet's atmosphere is compared to its radius. That's it. So there is no like lower limit as such. Okay, so for different planets, it can be different. And this scale height will answer that actually. So if you compute the atmospheric scale height, that will determine how big the atmosphere of the planet will be. And that you can use that to see if the planet's atmosphere is feasible. For atmospheric characterization, to study the planet's atmosphere, is it possible observationally? We can study it. So we compute this particular like parameter, atmospheric scale height. So if you want to compute this for the Earth, how would you do that? So scale height of the Earth's atmosphere. So we generally take Boltzmann constant is a constant. We know that 1.38 into 10 to the power minus 23 joules per Kelvin. Temperature, we can take the average temperature that we experience on the Earth, that is 288 Kelvin, 15 degrees Celsius. and G 9.81 meters per second square. And then here, the important term here you will notice KT by mu G, the mean molecular weight, atmospheric mean molecular weight. Now, this is very crucial because that calculation quite be difficult because that depends on the composition. Now, the Earth's atmospheric composition is 78% nitrogen. That is if you compute the mean molecular weight, 28 times the mass of proton for nitrogen N2. Then oxygen is 21%. That is 32 times the mass of proton and argon. So the other gases are very limited. CO, there is some CO2, there is some water vapor, but the most prominent of them is argon. So that is why I'm just taking remaining 1% as argon. So it's an approximation, which is all right to do. If you take other gases, CO2 exact also, the result won't change much. So that gives you 40 times the mass of the proton. And if you do this calculation total, this gives you 28.96 the mass of the proton. And if you substitute this in this KT by mu G in mu, then you get the Earth's atmospheric scale height as 8.4 kilometers. Okay, so in a sense, most of the Earth's atmosphere you can say is contained in this 8.4 kilometers. So basically, the pressure decreases by exponentially as you go higher in the Earth's atmosphere. So most of the Earth's atmosphere is contained in this 8.4 kilometers. Okay, so now this is Earth's atmospheric scale height. Okay, now there is a quiz that is coming for you. Now, if you do the same calculation, if I tell you that there is a planet called hot Jupiter, which is a massive planet, which is made up of 85% hydrogen and 50% helium. So, and I'm giving you temperature also. So could you all please just compute the scale height of this planet, a hot Jupiter planet, and type your answers in chat. Okay, so the question I have is, how is the planetary temperature in this equation determined? Is it assumed to be constant? Okay, so initially, so the first guess you can get is using the equilibrium temperature, what I mentioned. So you can use the size of your host star, the distance between the planet and the host star, and using that you can compute the temperature. Now, if you go for Earth, then in the case of Earth, we know the Earth's atmosphere, so we can accurately determine. And in the case of Earth, we can actually just go out and measure also. So that is how you get the temperature. But one thing you can say is the temperature varies. But in this case, we are more or less interested in the average. Because here we don't need the exact number. You will need the scale, how big the planet's atmosphere will be. So we don't need the exact numbers here. So one question, how much does the scale height of a planet go along with a tidally locked planet? So Harshita, I don't quite understand that question. What do you mean by that? You can retype or you can actually unmute also. How does the scale go along with the tidally locked planet?
Hi, sir. I'm Harshita.
Yeah, go ahead.
I just wanted to know, since for a tidally locked planet, like the temperatures of both ends are completely different. I was just wondering, so how the scale height matters in it. So
yes.
So I assume it's not going to have a constant scale height all over the planet. So will it change according to its position in the orbit?
Yeah, so that's a good question. So I understand. Okay, so I have a first. Okay, so basically, that's a very good question. So you are saying basically a tidally locked planet has a permanent day side and permanent night side. So already you have talked about what I'm going to speak about. You have asked that. So in that case, the temperature will be different. So here temperature is 1500 Kelvin, then in the night side, the 1000. So definitely the scale height will be different. So you're correct in saying that the extent of the atmosphere will be different in the day side. So actually you can see that even in the Earth. So if you come near the equator and if you go to the poles, the height of the Earth's atmosphere is different just in the equator and the poles because of the amount of means it's the full structure of the Earth's atmosphere, but it's the amount of radiation that is coming in the total dynamical balance. So so basically, yes, the scale height will be different if you compute it for the day side and the night side. In short, to answer your question. Okay, so so I'm starting to see the answers coming out. Okay, I'll just give 1 more minute and then I'll tell what the answer is around. Okay, so one question is there, why do we take Boltzmann constant in the calculation of scale height? Okay, so for that, I'll tell you. So if you look at the derivation of scale height, actually the derivation of scale height comes from something called the derivation of hydrostatic equilibrium. So I'm just throwing some words at you. You can look into this any atmospheric science book. So in that hydrostatic equilibrium, when you try to relate pressure, density, temperature, in that case, our ideal gas law comes into picture. And in that case, the Boltzmann constant comes into picture. And that is where the scale height has that is why the atmospheric scale height has Boltzmann constant in it. So yes, it's a constant, but it is because of the combination of the hydrostatic equilibrium and ideal gas law that is needed for the computation of the scale height. Boltzmann constant comes into the picture. Okay, so I can see many answers coming in. So I think all of you are forgetting a fact. So it comes, so the most accurate answer I can see is 573 kilo. So earlier the first answer was also 570. So it comes around 570. So it comes around 573 actually if you do the calculation. Okay, so basically, yeah, I can see many of them now coming to that. And those who are getting 900 or 1000, maybe you're missing a factor of 2 somewhere or something like that in your calculation. So, but the main thing to take away from this is look at the scale height of Earth's atmosphere, 8 kilometers, and look at the scale height of hot Jupiter atmosphere, 570 kilometers. Is so much massive. Like how much it is, 10, 50, 60, 70 times, more than 70 times more, not massive, I should say, the extent, the 70 times more larger atmosphere. The hot Jupiter has 70 times more larger atmosphere than that of the Earth. Okay, so that is what makes actually hot Jupiters and what we say warm Neptunes the best targets for atmospheric studies of exoplanets. Okay, so these are one of the best targets when you want to study the planet's atmosphere. So initially when the planets were detected, these were the first targets we started looking into, because we knew that these planets would have a bigger atmosphere, and so we can characterize them. And that in that first paper I told you, showed you know the Charbonneau one, where it is HD 18973, that's an hot Jupiter planet. That is why these targets were chosen, because these planets we can study their atmosphere. Okay, so moving forward, so here you get around 570 kilometers, and you now know why, and that is why we like try to study our targets that we choose for atmospheric characterization mainly involve hot Jupiter and warm Neptune planets, because their scale height is very large. Okay, and so these planets, hot Jupiter and warm Neptune, have many other important properties that can be helpful. First, they are very close to their host star, so that is why the detection is easy. So many of the exoplanets that we have detected are hot Jupiter and warm Neptune, because they're very close to their host star, so making detection easy. So that's why we have the planet, we can study the atmosphere. Then their scale height is larger, as you did the computation around 570. That's very high, so you can study their atmosphere. And you can see here I'm showing you. Like this is our solar system, Mercury and Earth. So that hot Jupiter can have 5, 3, 10-day orbit. So it's very close to its host star. And it's called hot Jupiter because these planets are very big as Jupiter, but their size, their temperature is very high. Our Jupiter is cooler, but their temperature is very high. And the other important property here, you can see this funny diagram. So this directly connects with the question that was asked earlier regarding tidal locking. Because these planets are very close to their host star, they are tidally locked actually. Means theoretically you can prove that they will be tidally locked because they are very close to their host star. So what does tidal locking mean is, basically you can see from this picture you can understand, like moon is tidally locked to Earth. You always see the same side of the moon, and similarly this hot Jupiters will always have one side permanently facing their host star. So you have a permanent day side and a permanent night side. That is basically meant by tidal locking. So that happens for the moon because moon is very close to the Earth. Similarly, this happens for the hot Jupiter and warm Neptune, which are very close to their host star. So this has a lot of implications in studying the atmosphere. One is the scale height is larger. Okay, and tidal locking, we have permanent day side and permanent night side. Okay, so that being said, now we know. So we started with we found exoplanet. Then we have 5,000 of them. So we want to study only them which are suitable for atmospheric candidate, because we can't study all of them because it's not practically possible. So there we computed the scale height, and then we move and we found that hot Jupiter and warm Neptune are very good targets. So we choose them. Then we move ahead. Okay, and scale height is one factor to study the planet's atmosphere. There is one more factor, which here I'm showing you one of the plots from my paper. Here you're showing a plot where on the x-axis you have the scale height, one scale height observable transit signal. So basically this is a proxy for the scale height you can think of. And the other important factor that is that will determine if the planet's atmosphere is observable, or you can detect the planet's atmosphere or characterize it. It's the number of photons that are coming from the host star, or basically signal strength, or you call it SNR, signal to noise ratios, and that is governed by the magnitude of the star. So here you can see the plot in K magnitude and V magnitude. Basically they represent the different wavelengths at which the stellar photons, we can get the stellar photon. So K magnitude corresponds to 2.2 microns and V magnitude corresponds to 0.55 microns. So basically higher the basically in the, and here the scale is different. So if someone in I think Ajit might have talked about stellar magnitudes. So in that case, the lower the number, basically you get more photons. So basically this region is our optimum region. Higher the scale height and lower the magnitude, because then you get more photons from that star, and that will be attenuated by the atmosphere, and we can detect here on Earth using telescope. If the star is not that bright, means lower magnitude, then you don't get sufficient photons and you're not able to reach sufficient SNR, that is signal to noise ratio, and then it becomes very challenging to constrain the planet's atmosphere. So you need quite a large number of photons to achieve a reasonable SNR, plus you need to have a sufficient big atmosphere. So that is how you, and those will be the best targets. So all the targets that lie in this part above this are can be said to be the best targets for atmospheric characterization. Same in this part. And why am I showing you both? Because stars can have different spectrum. Some might peak in some wavelengths, the other might peak in some other wavelength. So depending on the stellar spectrum, the best targets can change. Depending on the means, if an exoplanet is around a G-type star like that of the Sun, or if it is around an M-type star, the peak in the number of photons can change because of the Planck's emission, and that will change which targets will be best around which stars. Okay. So that also becomes important. So the main takeaway point should be, so the two factors that become important to determine our targets are a bigger atmosphere, so larger scale height, and a sufficient number of photons, so lower magnitude. So strong, like bright targets, we say that in general language, bright targets are good. Okay. So I can see some questions. Yes. So a question. Okay. Question: why is the value we calculated so off from 100 kilometer? Why is scale height really telling us? Okay. So basically, yeah, so Bruno answered it correctly. So atmospheric scale height is the height where the pressure drops by factor of E. So basically it tells you, so it's not, so factor of E actually is the exponential. Okay. So just to, so basically what we can interpret from the scale height is, and what basically most of the atmosphere is contained in which, how much part of the atmosphere. Okay, so what I should say accurately, so the Earth's atmosphere is contained in, most of the Earth's atmosphere is contained in this 8.4 kilometers. But if you go for hot Jupiter, the exponential drop, 1/E drop, happens at 570 kilometers. So that can basically be a proxy for the extent of the planet's atmosphere. In that sense, you can think of. And one more question that I see is, life possible on tidally locked habitable planets? It can be, it cannot be. I don't mean it is possible, definitely. Some people speculate that if it is too hot on the day side, on the night side, the life might be possible. So yes, it might be, but not on hot Jupiters. Okay, the planets that we are currently looking at, hot Jupiter and warm Neptune, they are very too hot. Like 1000 Kelvin, 1500 Kelvin is too hot for life to form. Okay, so moving forward, so now what we did is we found our planet, we determine our best targets. Then what we do, we apply for telescope time. So it's not like we can observe any target we want. Of course, if you have your own telescope, you can do that. But most of the state-of-the-art facilities like Hubble Space Telescope or a very large telescope in Chile, these facilities are oversubscribed. Means everyone wants to use that for their observation. It can be for cosmology, galaxies, and different. So they are oversubscribed. So you have to present your science case, like why I need to observe this planet, why it is important, how this planet has a big atmosphere, and we will be able to study this. So that's why your previous calculation of scale height and the magnitude, all those helps that you can say for sure this planet will have an atmosphere. Of course, you cannot speculate, it might or may not have, but there's the possibility. And if the science committee is convinced, you get time to observe on those telescopes. And then once you have, if you get time, then what do? You get your raw data. So raw data is in this form. So ultimately, the data that you get is in number of photons or radiances. So this is like the image one from the Hubble Space Telescope of one of the planets so actually what you do is look at the star, and then planet is going in front of the star. That will perturb the photons that you receive. So this is what the raw data looks like. And this raw data is then processed. There are many steps to that. So I'm just listing the steps here. Each of the steps is like involved. There's like dark, bias, flat correction. So this is basically the basic correction that we do in any astronomical image. Then you have to do the extraction of the spectra. Now here you're collecting this on a CCT that has come through a prism. So that you have to do spectral extraction. Then you do wavelength calibration. Then you do the white light curve extraction. What does that mean is like when the planet is going in front of the star, that dip in the brightness, that is called white light curve, because here you are combining all the wavelengths. You do all the corrections, then you bin, and finally you get the spectrum of that planet. And I'll show that what does that spectrum represent. So spectrum means basically the light that we receive from the host star that is coming through the planet's atmosphere, that is separated in different wavelengths. So this observational data reduction pipeline itself has many steps, and this has to be done in very carefully, and it takes a lot of time to that. Many people just do their PhD for developing this kind of pipelines. Okay, so this step which I mentioned about observational data reduction pipeline. So in this thematically or schematically, we do something like this. We get there is a star. The radiation is coming from the star going through the planet's atmosphere. And then we capture it using telescopes here on Earth, which separate, and these telescopes have prisms. In a short, prism is like separate them into different wavelengths, and that we capture here on Earth. And depending on what gases are present in the planet's atmosphere, there will be bright or dark spots. So if something is missing in the spectrum, it means that that has been absorbed in the planet's atmosphere, and that particular molecule is present in the planet's atmosphere. So that is how you can determine what's present in the planet's atmosphere, which gases are present. You can determine its atmospheric composition. Okay, so this is essentially what we do, and this is basically called transmission spectroscopy, or the spectrum that we obtained is called transmission spectrum. Okay, so you get this radiation from the host star going through the planet's atmosphere. You detect using a telescope, separate it into different wavelengths, and then obtain the spectrum. Okay. This is what I tell you conceptually, but in reality, what do we actually measure? In reality, this animation shows what we actually measure. So in reality, what we measure is the radius of the planet as it goes in front of its host star. Okay, and that we do in different wavelengths. Okay, so you can see the animation. If the planet, so here, let's say planet is going in front of the host star. Now it can have different gases in the atmosphere. Now, suppose if you see the planet looks bigger, which means its radius is bigger in a particular wavelength, which is this one. It means that above in the planet's atmosphere, there is some gas that is absorbing at 2.3 microns, and that is why the planet is looking bigger. And that is how you can determine if that particular gas which absorbs at 2.3 micron is present in the planet's atmosphere. Similarly, if there is a dip is smaller, then basically the radiation has just passed through it. It was not absorbed, and you can say that that particular molecule is missing in the planet's atmosphere. So that is how you can determine, using this transmission spectrum, the atmospheric composition of the planet. And as I'll come in the coming slides, it's not just atmospheric composition. We can determine the abundances, even the temperature, and many other properties could be constrained using this transmission spectrum. the different processes. Okay, so that's why this technique has been very powerful for exoplanet atmospheric studies, for atmospheric characterization of exoplanet. Okay, so I think I can take questions. So can't we use HARPS espresso data to understand exo-atmosphere? Okay, so HARPS and espresso, they are mainly radial velocity surveys. Okay, so in the radial velocity surveys, what we use very narrow wavelengths. So in that case, their aim is different. Their aim is to detect planet. So in that case, you need to achieve the required SNR. Only then you will be able to study the atmospheres. So, but people still use high resolution spectroscopy. So it can be possible. Isn't diffraction grating better and used instead of prism? So yes, Bruno, you are correct. So here, because I don't want to go into the details, I am telling it as a prism, like, because that's in our nominal school language, we say prism. But if you want say in the technical terms, yes, it's a diffraction grating. So it's a grism, basically. The term is called grism. So if you look at the documentation of James Webb Space Telescope, Hubble, the word they use is grism. Okay, but generally in our common language we use prism, so that's why I've been using prism. Okay, and Harshita is answering that question, like HARPS is for radial velocity and espresso can be used for studying atmosphere in the air environment. Okay, so thanks Harshita for that. Okay, so moving forward, so I hope you all understood about transmission spectroscopy, because now we are using this, we can study the planet's atmosphere. This is quite powerful technique. Okay, so so using that technique, what do we get? So here I'm showing you a plot of actual transmission spectrum for an exoplanet at HD 209458b. So what you're seeing here is on the x-axis you have the wavelength in microns, and on the y-axis you have RP by RS, which is the radius of the planet relative to its host star. Okay, so here what you're ultimately measuring is the radius of the planet, how it is changing with respect to wavelength that you're measuring. So you see here all like the points and the dips, and this is coming and going up and down, all these things. So you can dips and what you say the bumps and the dips, all of you are seeing in the spectrum. I'll explain what each of this means. Okay, and there is an error bar associated with it, because each of the when you measure, there are so many corrections or errors that come into picture. Like the first of all is your instrument noise. There is instrument noise. Then there are the instrument itself, like for Hubble Space Telescope, there is a change in the temperature because it comes in the day and night sun. So all that adds to your noise. Okay, and that gives to the error bars, like how precisely you are able to measure your radius of a planet at a specific wavelength. So that gives rise to this error bars, because only then we will be able to tell like how accurately we have detected something or not. Okay, so now the main point, so this is how the spectrum looks like. But what does this mean? How do we interpret which gases are present? What does this tell you? So in this case, we need to start and go into the depth of models. Okay, and just to point, this is for a exoplanet HD 2045, which is 159 light years away. Imagine earlier we were talking Proxima Centauri 4.5 light years away. This is 159. So there is such so far away, and still we are able to measure that. So that's we can say that's commendable. I should say, like we are able to measure the atmosphere of a planet that is so far away. And it's a sun-like star, and it's like 3.5 day orbit. So it just its 1 year is 3.5 days. It's so close. So imagine like if you're in this planet, you can celebrate your birthday every 3.5 days. So just to think in that sense. Okay. So once we have this transmission spectrum, how do we understand what does it tell you about the planet's atmosphere? Okay. So here we need models. We need theoretical models to understand what's there in the planet's atmosphere. So we bridge the gap. So we have observations, we put models, and then we get the full interpretation. Okay, so this is what the full interpretation looks like. Okay, so what does a model mean? So atmospheric modeling means everything you have in the atmosphere, you have to write in the form of equations so that you solve for it using supercomputers or computer to determine what can be there in the planet's atmosphere. Okay, so you simulate the entire planet's atmosphere. So this is what you can think of all the weather prediction models, climate prediction models on the Earth use. So if you want to get climate prediction, weather prediction for tomorrow, it will rain or not, or how will the winds will be, temperature will be. So these are where basically climate models. So they are three-dimensional climate models. So similarly, atmospheric modeling, basically you need to simulate each and every process that happens in the atmosphere. You need to simulate, as I'm showing, radiative transfer, how the radiation is going through the planet, how it's interacting with the constituents of that. Then there are clouds in it, how it interacts with the clouds. Then lightning, volcanoes. If there are biology, if there are humans or animals, like the gases that are emitted, all those things, plants, everything actually should be included. Ideally, should be there in your model, but it's not that easy. So it has different like components: chemistry, radiative transfer, opacities, clouds, dynamics. All of these things come together, make a model. So basically, you want to simulate entire planet's atmosphere. That is your ultimate goal. But frankly speaking, it's not that easy. The complete model is difficult. So we take small and small steps. So the more and more complex you make the model, more difficult it becomes to solve them. So essentially, atmospheric models you write in form of equation and solve them using supercomputer. That is essentially what atmospheric modeling of exoplanets is. Okay. So what's there in these models? So I am talking about many components. I won't have time to cover all the components, but I'll just cover the main components that that become important. So one is the chemistry. Okay. So so using these models in the first the first step, you have to predict what might be there in the planet's atmosphere without even knowing. You have some basic knowledge, like you know the distance from the host star, you know how bright the host star is, what is the temperature of the host star. Using that, you have to determine. So here there are some chemistry mechanisms or techniques that we can use. So especially, as I said, hot Jupiter and warm Neptune are the best targets currently for atmospheric studies. So in this, actually, how do you compute the chemistry of the planet's atmosphere? So there is something that we can use called equilibrium chemistry. So what does this fundamental mean is, if suppose you have a box at a certain temperature and pressure, and if you put certain elements in that, what will be the final outcome? Which molecular species will dominate? Like here I'm showing an example of a reaction called carbon monoxide plus hydrogen H2 in the molecular form, and the output will be methane plus H2. Now, depending on the temperature and pressure in the planet's atmosphere, either the reaction can go forward or backward. So for hot planets, like here for stars and brown dwarfs or hot planets, the reaction is dominating backward. So the dominance is carbon monoxide and hydrogen. And that is what we see. Stars and brown dwarfs and hot planets are dominated by carbon monoxide and H2. But when you come to the colder planets like Jupiter, in that case, methane and water vapor also dominates. In that case, of course, I'm not talking about the background atmosphere. Background atmosphere in both the cases is dominated by hydrogen and helium. I'm talking about the constituent, like the minor species. It is the methane and H2O that is dominating. So I'm showing you just one reaction. So such reactions can exist for many such molecular species that can exist. So hundreds and thousands of this reaction, and that the combination of that can give you what are the possible chemical species that can exist in the planet's atmosphere, and that you can determine by the chemistry. So here I'm talking about giving a technique called Gibbs energy minimization. And by using that technique, you can compute the equilibrium chemical abundances. So I won't go into the details of that, but if anyone is interested there, you can contact me or basically look about the Gibbs energy minimization, how this calculation is done. Okay. Then the next thing is, once we know what's there in the planet's atmosphere, where do chemical species absorb and how much? Okay, so here this is one of the most important things that we need any model, and this is actually forms the backbone of all astronomical calculation. If you think, this is what we term as opacities, because unless we know where different molecules will absorb, unless we don't know their fingerprints, we can't say if that particular molecule is present. Like I was telling in the computation of transmission spectrum, we need to know the fingerprint, where different molecules will absorb at different temperature and pressure. And this applies even for like if you want to study exoplanetary atmosphere, if you want to study stars, even if you're studying galaxies, everywhere you need this opacity. So this is why where do different chemical species absorb and how much. So for this, we need to do this heavy calculations of because this where do different species absorb and by how much is dependent on temperature and pressure. And the effects of the broadening, natural Doppler, pressure broadening, all of this has to be taken care into account. So this whole is termed as opacities, and that needs to be there in your model. Okay, and finally you combine all these things, and this is just a brief slide. I won't go into the details because this is quite involved. So you solve for the radiative transfer equation, compute compute chemistry, compute opacities, and you do this under some physical constraints of hydrostatic equilibrium and energy conservation, and that ultimately will give you a pressure temperature structure, and that structure you can use to compute the theoretical spectrum of the planet. And once you have the theoretical spectrum for different parameters, you can fit that to your observed spectrum. And finally, you get this, which is the interpretation of your observations. So here you are seeing the interpretation of HD 209-458b transmission spectrum. Again, you have wavelength on the x-axis, the same. You can see earlier we just have observation point. Now I'm overlaying a best fit model to that. So here you can see the models, what models have given us. It has given us so much information about the planet. The first information that we can clearly see is this Rayleigh scattering slope. Okay, so what is Rayleigh scattering? The reason why we see our sky as blue, it is because of this process of Rayleigh scattering, which has lambda to the power -4 dependence, like wavelength to the power -4 dependence. Okay, so as you go higher in the wavelengths, the Rayleigh scattering decreases. You can see this slope here. Basically, this is the Rayleigh scattering that we see in the planet's atmosphere. We are seeing this process. Then we see sodium. We can see a sodium feature here. We have detected sodium in this planet. We can see potassium. Okay, I'm labeled them according to their colors. Like sodium is same. Like earlier we used to have this light, no, sodium vapor lamp lights. In some places it's still there. That is sodium. So sodium, potassium, and then water. We have detected water vapor also in this planet. So at 1.4 micron, you can see that there is a sudden increase in the radius, which says that the planet is bigger in that wavelength. So you have detected water. Okay, so we have detected Rayleigh scattering, sodium, potassium, water in the atmosphere of HD 20945. And here what we have done, we have taken our observations, we have combined, you developed our model, fit the model to our observation, and this is what is the final result. You get what's there in the planet's atmosphere, its atmospheric composition. You can get a handle over its temperature, Rayleigh scattering. All these properties we are able to learn, which for a planet which is 159 light years away. Okay, so that this indeed is a quite strong technique. We can think of. Okay, and so here when I talk about interpretation of observation, there are two actually different ways to do that. Now what I talked about is something called forward modeling, which is basically, imagine you have very few basic information of the planet, how far it is from the host star temperature, all that, and from that you develop your basic model, and then you interpret your observation. That is called forward modeling. You use your basic understanding of physics and chemistry. But there is an alternative approach where you have your observed spectrum, you have your model, and you relax many of the conditions in your model. Just you remove your like conservation of energy, and just do millions and millions of the simulation. It's called Bayesian, using Bayesian statistics or Bayesian sampling, and then try to fit to the spectrum. And in that case also you can get quite good constraints on the composition of the planet's atmosphere. So both of the approaches are equally valid, and both of the techniques have their own strengths and basically pros and cons, strengths and weaknesses. Both of the techniques have their own strengths and weaknesses. Okay, so I will take questions here because later I'll move on to topics. So
Sir, this is Krishna. I have two questions.
Yeah. Go ahead, Krishna.
Yes. So this project I'm involved in right now, I had two questions regarding that. So the project I'm involved in is also like detecting sodium using high resolution spectroscopy. So regarding your lecture, I had two questions. So the way, so does it matter? So as Dr. Ravi explained, there are different definitions for what you consider in transit and out of transit, right? There are two separate points. So I didn't see that much of a difference in the detection when I used a different definition of in transit. Like I used T1 and T4 as contact points instead of T2 and T3, which are different contact points for in transit. I didn't see that much of a difference. In general, would it make a lot of difference if we take a different in transit time while computing a spectra? That's part one of my question.
Okay, so you are saying in transit time. Okay. So here, so if I'm understanding your question correctly, so here basically you have your baseline. So if you want to measure your transmission spectrum, what you fundamentally do is you do that in multiple wavelengths. You have baseline. So when it is out of transit, and then you are in transit, and you ultimately measure the radius. Okay. So okay. So in that sense, so if you have sufficient baseline, I don't think it will matter. Okay. But that being so, if you have sufficient baseline and you want to understand planet's atmosphere, then it won't matter. But I'm saying but here, but that depends on your science problem. What are you trying to understand? If you're just trying to detect sodium, then definitely, I mean, from my understanding, it won't matter what time. But if you want to study the day side and the night, the evening and the morning side of the planet's atmosphere, like you want to resolve the planet, then the timing matters, because in that case it matters like which side of the planet comes first in. So in that case it matters. So fundamentally it depends on what is your science question. But if your science question is just detecting sodium, I don't think that would be a problem.
Okay, yeah, understood. Thank you. And just a small question. The errors you were talking about, so the way I propagated the errors was I just took square root of the flux, while some people treat photon noise as a Poisson distribution. What would you say is the most accurate way of depicting the errors when you have the flux data?
Oh, so means you mean for the transmission spectrum, you mean for that?
Yes.
So basically you're sorry. So you're talking about this the error bars that you see behind.
Yes, yeah.
Okay. So what method did you use, you said?
I just took a square root of the flux and I propagated the error, and it came very similar to when they treated it as a Poisson distribution.
No. So I would say at the first step, that is all right. Okay, to first extent. But ultimately here in this computation, the more because when you see develop this reduction pipeline, each of the steps keeps on adding its own noise, and all of that is propagated here.
Okay.
So it becomes a more complicated, but what you say in just like if you want to just approximate it to a certain extent, then you can do that. Okay. And here you have to be careful, because ultimately you're getting an error on the radius of the planet to that of the star. Okay. So that you get your error on the flux, and that is being converted to the radius of the planet error on that. So ultimately you're computing the error in your planet's radius in different wavelength.
Yeah. Okay. Thank you.
Yeah, no problem. Then there are some questions are there on are the errors of your spectral measurement computed at square root of the flux? No, so they take into, it's not just the square root of the flux, they take into account all the different effects and the systematic corrections that, okay, someone should mute them. And then second, what are the softwares used to reduce the spectral data from? Okay, so the softwares are generally, many people develop their own pipelines. Okay, so until a certain level, like so there are many stages of this. Up to certain stages, the telescope facility, like the people who operate the Hubble Space Telescope, something, they have their own pipeline until certain levels. But after that levels are crossed, then you have to develop your own reduction pipeline. Like they can do in this, they might just do the bias and correction. This step they might do, but after that you might have to do everything. So it depends on which telescope it is and how they are. So many of people develop their own custom pipelines. Okay, is the transmission displayed just the planet spectra? Okay, so actually, so it's just a planet spectra. So it is, in a sense, it's a planet spectra, you can say, because here you are measuring the radius of the planet with that of the star. But it in principle, it includes both stellar and planet measurement, because ultimately what you're measuring is the photons that are coming from the host star going through the planet's atmosphere. Okay, so that is ultimately we are measuring. But what we are dividing, because we are dividing by the host star radius, and assuming that it does not vary that much, we are reducing its effect. But that could play a role. Like if there is star spots or something, it could play a role. Okay. Yeah, so Priyatam, exactly. So is there no host star activity? Yes, there can be. So in fact, in the HD 20945, it's not there, but if there is some stellar variability, like if stellar, there are star spots or there are faculae, the spectrum can change. So in that case, it can become challenging. So the targets, okay, so it's good you asked this question. So the targets that we choose for atmospheric studies also initially were low activity stars. If they do, they are mainly, if the star does not have much activity, they are good targets. If they are more activity, they can mess up your transmission spectrum, and it can become difficult to characterize the planet's atmosphere. So yes, variability can play a role. So someone is asking about ML. So yeah, means ML can play a role because these computations are quite time consuming. So you can use ML to use grids of model. And then but transit of Venus and Mercury doesn't occur frequently so far. Yeah, so that's a good point. So, but that is for Venus and Mercury. Okay, but for these planets which are very, very far away. So and as I said earlier, these are hot Jupiter. So they quite frequently target their host stars because they're quite close, 3 days, 5 days. So the frequency is quite good. Only one thing that matters, it should be observable from the Earth. That the plane, we should be sure that you should be able to see the transit. Okay. For forward modeling entry, which open softwares do you think are accurate to use it, or is it best to build your own model? Okay, so Sakshi, so the models that you have mentioned, Petit Trans, Platon, and Taurex are all good. So if the software is published, then it has gone through peer review, so they are good. And if, of course, if you have sufficient time, you can build your own model. That is always good because you learn a lot from that. But building your own forward model is not that easy. It takes years of work. So Petit Trans, it took a full PhD. Paul Mollier, who developed this. Platon, almost 2-3 years of work. Taurex, developed by, so these all models took 3-4 years of work, and that too by 3 or 4 people. So these are it's a group effort, and it takes a lot of time. So, but if you're curious for your PhD, you can develop this, or at least the simplest form. Okay, and each of these models have their own pros and cons. Some can do something, some cannot do something. Okay, so depending on your application, you can develop. You can say you can develop a model for transmission spectrum. You can take things from other softwares and use that. So depending on your science problem, you can develop your own model. Okay. So that being said, I'll move ahead because there is a lot to cover. As I was saying, we're talking about the transmission spectrum, and I mainly spoke about hot Jupiter and warm Neptune and the models and interpreting them. So you must be thinking, yeah, why don't we try this for Earth-like planets? So yes, we have tried this for Earth-sized planet. So the TRAPPIST-1, 40, which is just 40 light years away, which is become very famous. We have almost so many systems, like 7 planets we have in the system. Many of them similar to size of the Earth. So so this was one of the, when this was discovered, where everyone was very excited about this, and people started thinking about like, how can we characterize this, and people started submitting proposals to observe this using Hubble Space Telescope. So yes, we have attempted characterizing TRAPPIST-1 system using transmission spectroscopy, but the results have been very discouraging. We can see all the spectrum that we have received is almost flat. So you can see here TRAPPIST-1, D, F, E, G, all the spectrum that we have received is almost flat. Basically, you can't tell anything. So what does this imply? What does a flat spectrum imply? So generally in the transmission spectrum, the flat spectrum implies presence of clouds, or more possibilities that the atmosphere is very thin, or the extent of the atmosphere is not that much. Or in other words, your transmission spectroscopy is not capable to do that, because I'll come to that in a few slides. Like, what are the limitations of transmission spectroscopy? So if your atmosphere is very, like, not like hot Jupiter atmosphere might be very big, but if your atmosphere is very small, then your transmission spectroscopy won't be able to probe this, and you might get a flat spectrum. So D, F, E, G, all the TRAPPIST-1 we tried using Hubble, and we got a flat spectrum. So the atmospheric characterization using transmission spectroscopy for Earth-sized planets have been very challenging, and we have not been able to do it. So that is one future we are trying to move towards. So how many systems have we found using multiplanet? There have been many. I don't know the exact numbers. And then do you undertake forward theoretical modeling or inverse in your work? So in my work, I do both. So because I said they have their own benefits, and so I do forward theoretical modeling also, and I relax some conditions in my forward model and use that itself as the inverse model. So yes, I use both of them. Okay, so moving forward, So initially I was just talking about transmission spectroscopy. Now I'll talk about something called emission spectroscopy. Now, what does this mean? So yeah, we looked at, like, this is suppose your host star. The planet is orbiting his host star. So when the planet goes in front of the star, this is called primary transit. Okay. And now you can see for the geometry, when you're in the primary transit, you're measuring the planet's atmosphere. You're just looking at this annulus region. So this annulus region is called the limb of the planet, which is basically like, you can think of the day-night terminator region. So that is like, if you take a sphere and cut it in between, what do you see? That cutting, that the cross section, that is the only part you can measure. So that is one thing, that is the limitation of transmission spectroscopy. Okay. And then, but how do you measure the hemispherical part? So in that case, the method of emission spectroscopy comes into picture, or that can be beneficial. So in this, what we do is, when the planet is revolving on its host star, just before it goes behind the host star, we have planet plus star, the photons coming from both. We have flux from planet plus star. And as soon as the planet goes behind the star, we have just the flux from the star. So planet plus star minus star gives you planet. So that is how you get the planet spectrum, or planet's emission spectrum is measured. So that here you can get a direct signal from the planet actually. When you do transmission spectroscopy, actually you're measuring the stellar flux or stellar photons going through the planet's atmosphere. But in the secondary eclipse or in emission spectroscopy, you're directly measuring the planet's flux. So that is and the other thing is, you are measuring the day or night side of the planets in emission. So that is very strong. You can get a very constraint on the day or the night side of the planet. But if the planet is tidally locked, like the hot Jupiter we talked about, in that case you get the day side, because as this is a star, as the planet is going behind, the side that will be facing you is the day side. So you get the flux of the day side of the planet in the when you do the emission spectroscopy. Okay. So that being said, so I will have now one more quiz coming in. So in the, as I said, the geometry in the transmission is this. Okay, you have a, suppose this is a tidally locked planet. This is where the star is there. Okay, and that's why this is bright. You measure the radiation coming in, and you measure here and somewhere on Earth. So this is the whole atmosphere it goes through for transmission, and for the emission it goes through this. Like, this is what you go when it is just behind the star. Okay, and suppose the height of the atmosphere is 3 times the scale height. Okay, so the quiz is, how much distance does the electromagnetic radiation or the radiation traverse through a planet's atmosphere for transmission and emission spectrum reaching Earth? So basically, I'm asking how much part of the atmosphere does it travel when we look at the radiation for transmission and when we look at the emission. Assume the planet's atmospheric scale height as 200 kilometers and radius as 8,000 kilometers without including atmosphere. So this is very simple. So how about in 2 minutes, you can send your answers in the chat.
Dr. Goyal,
Yes.
can you please once again explain how the emission spectroscopy, in what perspective it is important compared to the transit spectroscopy? What signals we cannot capture in transit and we capture in emission? I was a bit lost there.
Okay. I'll do that in a second. I think this quiz is to answer that question. Okay. So I'll once you do this quiz, I'll again explain why transmission emission is in what sense emission is beneficial in 1 or 2 slides. And if you don't understand that, then you can again point that to me. Okay. So here this should not take much time because this is simple Pythagoras theorem, I guess, that you have to apply. Okay, so that is good. So Akash is giving it. So for transmission 3600, emission. Yeah, so emission will be basically, actually the scale height is 200, so it will be 3 times of that. So 600 kilometers, and the transmission comes around 3200. It's close. So the main point to take away here is, see the path length. Sorry. So the main point to take away is the path length. Okay, so the path length that the beam of radiation has to travel through the planet's atmosphere is 3000, almost 3200, 3000 to say almost 3000 kilometers, and here in emission it's just 600 kilometers. Okay, so in that case, you have to travel a lot of atmosphere. Okay, so that is why you cannot go much deeper in the planet's atmosphere when we are doing transmission spectroscopy. You cannot go much deeper in the atmosphere. So here the plot shows that, in a sense. Here I'm showing the pressure temperature structure of the planet. You have temperature on the x-axis and pressure on the y-axis, going from high pressure below to low pressure above. So that is how the planet's atmosphere is like. So in the transmission, you cannot go much deeper because it will be like saturated. You can think of that. The light won't be able to go. The optical depth becomes so high that it won't allow the stellar radiation to pass through. So you can't go much deeper. But in emission, because that radiation is coming from the planet itself, it has to traverse a less part of the atmosphere, so you can probe deeper in the atmosphere. So you can get information about the deeper atmosphere using emission spectrum. So this is one of the major advantages of emission spectrum. First, you get to see the light of the planet itself. So the planet's information is directly imbibed in it. You don't have to worry much about the planet's how the optical depth, because the planet's optical depth in transmission, as you go down, you cannot go much below a certain height. But in emission spectrum, you can probe a wide range of pressures or a larger part of the planet's atmosphere, which you cannot do in transmission. Okay, so that is one of the major benefits. And the other benefit is you can get accurate constraints on the temperature, because in the emission spectrum, what you are measuring is the direct flux that is coming from the planet. So you get the most accurate constraint on the temperature, which is not with the transmission, because in the transmission you are measuring the flux that is coming from the host star. So it has the information, the photon, the energy of the photons depends on the temperature of the host star. But in the emission, you are using getting the flux from the planet itself. So you can get very accurate constraints on the temperature also. So this is one. These are the main benefits of using emission spectrum. The main is constraining the pressure temperature profile, pressure temperature structure, and I'll mention why that is important. So Sakshi, does that answer your question or?
Yeah. Thank you so much. I understand.
Okay. Yeah. Okay, so the emission spectrum can be very beneficial, okay, in understanding the planet's atmosphere. So this slide shows you that. So that's why I'm naming it deconstructing the emission spectrum. It has a lot of information about the planet's atmosphere. Like on the right hand side, you can see a plot of, on the x-axis you have wave number or wavelength. It can be just proxy. Means on the top you have wavelength and the bottom you have wave number. And ultimately, on the y-axis, you have radiance, which is a proxy for the flux you can think of. Actually, specifically, this is the intensity of radiation. Okay. So here, what you see, this is actually the emission spectrum for Earth. Okay. And in this, what you see, first you see this dashed lines, which represent the black body spectrum at different temperature. And this is the spectrum of the Earth that if you measure using if you go at the top of the Earth's atmosphere, you measure, you will see something like this. So what you can see here is first of all, you can see different absorption features. You can see the absorption feature due to carbon dioxide. This is due to carbon dioxide, then due to ozone, water vapor, all these features you can see. And other is you can invert this to get the information of the pressure temperature structure. So, and why am I constantly talking about the pressure temperature structure? Because the pressure temperature structure of the planet plays a very important role in the climate of the planets and its weather. It governs the dynamics of the planet. So like, for example, like in the Earth's atmosphere, every day you see like the sun's radiation coming in, it heats the atmosphere. But if in the months of May, you have a lot of heating, so thunderstorms are formed. Now, this is basically the change in the thermal structure, and that makes thunderstorms form, change the weather. So this thermal structure is very important for considering the planet's weather and climate. Okay, so that is why this emission spectrum can help us constraining that. Okay, and this has been done for, we have tested this for one of the exoplanets. So this is for one of the exoplanet called WASP-121b. It's an ultra hot Jupiter. In that case, actually we detected an inversion layer using the emission spectrum of that exoplanet. So this has been quite a big discovery. This was the first detection of the stratosphere in an exoplanet. So, so using these techniques, we can actually detect exoplanet, like constrain the pressure temperature structure and detect inversions if the planet has inversion, like we have inversion in our own atmosphere. You can see the inversion we have in our stratosphere because of the presence of ozone layer. Okay, so this emission spectrum can be used to constrain that. So in the Earth's temperature, you can clearly see this ozone inversion, and this is what protects us from like harmful radiation coming from the sun. And it has many purposes. The ozone, this is a stratified, this is quite stratified part of the atmosphere, so very stable. So all our aeroplanes fly in this part of the atmosphere. Okay, just to give you one fact. Okay, so fundamentally, emission spectroscopy can be used to constrain the pressure temperature structure. Okay, so that should be a main takeaway point. And since I'm running out of time, I might have to go a bit fast. Okay, so emission spectrum of the solar system terrestrial planets you can see here. Okay, so this is in all of them, you can see one strong feature, it is CO2, because that's there in all the planets. But for Earth specifically, you can see this ozone feature and H2O features. Okay, which makes it a quite interesting and makes it suitable for life. Okay, so since I'm running out of time, I'll think I'll skip this part and keep more time for questions. Okay, so this is more about exoplanet phase curve, so I'll skip that. I'll more talk about a bit about the interiors. Okay, so when we think of the planet's atmosphere, so if you go to the fundamental question of where does an atmosphere of a planet come from? So there are three fundamental theories there. So you accrete it from the nebular gas during the formation, which leads to the primordial atmosphere, which is hydrogen helium dominated, because that is what our nebular gas has. Then the second possibility is outgassing from the planetary interior. That can lead to the formation of secondary atmosphere, which can be dominated by other gases than hydrogen, helium. And the third possibility is the volatile deposition via asteroids and meteoroids. Okay, so these are the three basic mechanisms by which planet can form its atmosphere or can have its atmosphere. So why am I telling you this? Because this has directly connects with the planetary interior. So this tells you how the exoplanet interior, the interior of any planet, plays in an important role in constructing an atmosphere, in shaping its atmosphere. Okay, so this is a very, very busy diagram here. The main thing to take away here is how do you, so initially we were constraining the planet's atmosphere. Okay, but if you need to constrain planet's interior, how do you do that? So here we are one basic, there are three ways to form a planet's atmosphere. Like primordial using accretion, then outgassing and volatile deposition. So suppose our planet has formed due to outgassing. So there will be some signatures of this outgassing in the atmosphere, and we can use those signatures to constrain the planet's interior. So that is one technique. And the second technique is the planetary mass radius relationship. So here what you're seeing a very busy plot with mass on the x-axis and radius on the y-axis. So what, depending on what the mass of the planet and the radius of the planet is, we can make a guess of its density. And using our theory of planetary interiors, we can determine what the interior of the planet might have. So in this plot, you can see Earth and Venus lying here, which are mainly lying in the regime between rocky planets and so between 33% Fe iron and 100% iron. We know that the Earth is not 100% iron, but lies somewhere between that. So these theoretical models of mass radius relationship, we call them, can tell us just using your mass and radius where these planets can come. So using this mass radius relationship and the present and measuring the outgassed gases in the planet's atmosphere, we can constrain also the planet's interior, because all of this will play a role in what gases will be outgassed. So this is how we can constrain the planet's interior also. That's why the atmospheric characterization we talked about becomes important to constrain the planet's interior as well, along with the mass radius relationship. Okay, just giving a brief like overview of how we can constrain the planet's interior. But as of now, all of this is mostly theoretical, because planet's interior is very challenging to constrain. But people have attempted using mass radius relationships, different exoplanets that we have detected, they have placed here in different regimes to get a rough estimate of where they what might be their interior made up of. Okay. So that being said, I'll just briefly take you through like what is currently the state of the art. I talked about the various techniques, transmission, emission, but where are we at currently? So earlier, all this for HD 209, earlier all these measurements were done using Hubble Space Telescope, which had a 2.4 meter, which is that, but the size of JWST is 6.4 meter in the diameter. So, and plus the JWST wavelength coverage almost goes up to like 30 microns compared to the Hubble, which was restricted until 1.7 microns. So that is a big leap that we are taking in terms of a wavelength coverage and the size. So that has helped us a lot in terms of exoplanet characterization. So these are the different instrument capabilities that have in University. I won't go into the details of this, but there are many instruments with different resolution, different wavelength coverage. So currently, just in last year, July, we started getting observations from the early release science program. So WAS39b was one of the early release science program. This planet was we selected for this observation because already in 2018 using Hubble, we had detected 3 water features in this planet in the transmission spectrum. So it was very good target. We knew that something is there in the planet's atmosphere. And that is why we observed this again using JWST, and we detected the carbon dioxide features in this planet. So this was the first confirmed like evidence of the detection of carbon dioxide in the planet's atmosphere. So earlier I was talking about so much about carbon dioxide, but earlier it was all theoretical. This was the first confirmed detection of carbon dioxide in the planet's atmosphere, in an exoplanet atmosphere, which was for WAS39, and that was for at 4.5 micron. And this was just coming out of the early release science. So these are initial results. Now more such results will come as we move ahead with because most of the planets that we have detected among the 5,000 are Kepler. So that is considered in one part of the Milky Way. Like as our sun is here, we were looking at one part of the Milky Way. All this is still unexplored. But and this is just I'm showing you the Kepler field of view, where you can see when you get night, you can see this Kepler field of view. Most of the exoplanets lie there. But and soon using TESS, we are doing a full sky coverage where we are looking at planets that are close by, and then we will be able to get more, we'll detect more exoplanets, and we will be able to characterize more such exoplanet atmospheres. Okay, so this is where we are heading in the coming years. This has already started. TESS is already operational, and we are detecting more and more planets each day. Okay, and atmospheric characterization initially we started with hot Jupiters and warm Neptune, as was saying, because they were the good targets. But slowly, as our instruments are getting better, as our techniques are getting, we are moving toward smaller and smaller planets, Exo, Neptune, Super, with the ultimate aim to characterize Earth-sized planets. That is our ultimate aim, but that is very difficult. As you can see from this plot, it's very difficult to characterize smaller planets because the smaller size of the atmosphere, smaller mass, all this makes it the SNR is the signal to noise ratio is small, which makes it very, very challenging. And the final thing is like the searching for unambiguous biosignatures. Like currently we means when you do atmospheric characterization, the important step is, can you characterize these planets accurately, and can you detect biosignatures if you want to detect presence of life? So getting first you have to determine what are unambiguous biosignatures. Like for example, I'm showing you oxygen. Now oxygen can be a good it has a biological source on Earth, but it has non-biological source also. Like by dissociation of water by UV, you can produce oxygen. And then methane has biological source from like biology, like I'm showing you the figure of the cows and all the paddy fields. That are the sources of methane. But there are non-biological sources also, which are the volcanoes and everything. So these things, you cannot say that they're definitive biosignature, but there are some definite biosignatures. I think there's a full lecture on that. I'm just giving a one slide here. So like dimethyl sulfide. So this is actually if cabbage is being cooked at your home, the smell that you get, that is dimethyl sulfide. That's why I'm showing you cabbage. So currently we only know that the biological source for that. Non-biological sources are not known. So these kind of species can be considered as a very good source of biosignatures. But the problem is then they should be present at detectable levels. Like our instrument should be able to detect it. They should be at sufficient SNR to be detectable. So these all problems make the atmospheric characterization to detect biosignatures on Earth-like planets very challenging. I already said that for Earth-like planets, we're getting flat lines. So imagine detecting such species. This is more challenging. Okay. So that being said, I'll just conclude with the basic take-home messages. Okay. So there are a lot of diverse exoplanets out there. Each can have different types of atmosphere. Hot Jupiters and warm Neptunes are currently the best targets, but soon we'll move towards smaller and smaller planets. Transmission spectroscopy can be used to constrain atmospheric composition. Transmission spectroscopy is very strong for atmospheric composition. Emission spectroscopy can be used to constrain pressure, temperature, structure. We have already done that for one of the planet WAS29b. We can use exoplanet phase curves. I did not talk about this because of the lack of time, but we can ask later if you have more time. to constrain winds and planetary climate. We can constrain the exoplanet interior using mass radius relationship and characterization of outgassing constituent. And these are the details, which I don't think is necessary now. If anyone has any questions of any detailed conclusions, I can go that in later. Okay, so I'll keep this and open the floor for questions because I want to give more opportunity for you to ask questions. Okay, so please feel free to ask questions. Okay.
So we request participant to raise the hand, and so we can take one by one. So
yes.
Participant, can you please raise your hand so that I can unmute, or we can go ahead with the questions from the chat box. Jayesh, can you hear me?
Yes, I am able to hear you.
Okay.
Yes.
Yeah. I think most of the questions you have answered during the talk. I think, yeah. Now, Sakshi has asked, could you give a short overview regarding the
unified model? Okay.
Yeah.
Okay, because we have time, I can do that. Okay. So this is the part I skipped. Those were 2 slides because I thought it will consume a lot of time. So the unified model, when I say, so this is the model developed by the UK Met Office. So these are called 3D GCMs, 3-dimensional general circulation model. So these are actually the most accurate models to model an atmosphere. Okay, so when I say this, so this is actually a model used for weather and climate prediction for the Earth. This is an operational model. So every day this gives you weather and climate prediction. So almost 50% of the Earth's aircraft weather prediction comes from this model, all of the Western Hemisphere. So these are all operational models. So they have very accurate physics, dynamics, chemistry inbuilt in it. But these are catered everything for the Earth. So what people have done it, there some research groups have adapted it. That is when I was doing my PhD, adapted it for exoplanets. And in this, we include dynamics, radio transfer, chemistry, clouds. All of this is included, and we adapt it for exoplanet atmosphere and run this model for those planets and see try to determine what might be the climate on that planet, what will be the weather, and we simulate their observational, transmission, emission, and reflectance spectrum. So these are all the characterized we try to simulate using this 3D unified model. So this is one of the most sophisticated models I can say. So Sakshi, does that answer your question? Short overview, or do you need more information in this?
Okay, so Dr. Jayesh, there is another question. I think Priyatam has asked, do you undertake forward theoretical modeling or inverse modeling in your work?
So in my work, I do both. So we have developed our own forward model. It's called ATMO. So that we use for, and I developed like library grids of models, which we use for interpretation. So here you can see in the JWST. So the first data that we came on, we used our model called ATMO, and we interpreted that. So this is the forward modeling part. And then we also then relax some of our constraints, like we relax conservation of energy. We don't use radiative convective equilibrium PT profiles. We use parametric PT profiles. And then that can be used as in the retrieval framework also, or inverse framework also. So yes, we do both.
Okay. Dr. Jayesh, there is a last question. Is JWST expected to detect atmospheres of Earth-like or super-Earths, and will this be through a transmission or emission spectrum, or both?
Okay, so is expected to detect atmosphere Earth-like or super. So yes, it will be definitely attempted. It is actually, as we speak, it is being attempted. So TRAPPIST planets have been observed, and people are currently we are processing the observation and trying to understand. So we are trying it, but when you say expected to, we don't know. So it's a challenge. So it might be able to detect, and mostly in transmission. In emission, this is very cool. So one thing I forgot to mention, emission spectrum, because we are measuring the planet's the radiation, the flux of the photons coming from the planet directly. The SNR can be challenging because the number of photons can be very less, because it's the planet's temperature is lower. So the signal to noise ratio becomes very challenging to do emission spectroscopy. That's why while transmission spectroscopy can be very successful there. So definitely using current trials are done using transmission spectrum, and we have got the measurements. We are processing it, and we don't know what we'll be able to get something, will not, we don't know. It might be possible, it may not. The coming 1 year will tell us actually.
Okay. I think Harshita has a raised hand. So because it's we are running out of time, Dr. Jayesh, can you share your email ID or something so that those who want to ask question, they can send it directly to you, and they
So
can
I
get in touch. Yeah,
am sending my email in the chat.
sure.
And I'll try to send answer the question, but as you might be aware, like we have so many requests email, so I might not be able to respond quickly. I might take a week or so.
Correct. So we request participant, like those who have questions, they can check the chat box. And Dr. Jayesh has shared his email ID. You can note down and send questions to him. Okay. So I think Harshita has a raised hand. This is the last question, and we can then wind up.
Okay.
Oh yeah, I just had a follow-up question. So you mentioned that during emission spectroscopy, we are just looking at the planet's flux, and so are we blocking the starlight through a coronagraph, or so?
Yes. No, so that could be done. So in this technique, what I'm talking about, in this we are not blocking it. Okay, so in this technique, the emission spectroscopy, this is in emission spectroscopy when in the planet is transiting. Okay, so but you could block using a coronagraph and also do that. But here we have to what we have to do it in that case, we need to be sure that the planet's flux is sufficient. So what you're talking about, that comes into picture when we do direct imaging. So if you're doing a direct imaging emission spectroscopy, so when I talk about emission spectroscopy in the talk only, I spoke about like in transit, but when you're doing emission spectroscopy for direct imaging planets, they might be very far, quite far away from their host star. In that case, you can block using coronagraph, and then you can retrieve the emission spectrum of the planet. So that also could be done.
Yes. So I was just stuck because you mentioned that the flux from the planet will be very less. So, but still, we will be receiving photons from both the star and the planet.
And yes, but we remove the stellar flux. So, but conceptually, both the emission spectroscopy is the same. Means if you do using a coronagraph, ultimately what you're trying to block the star, and you're blowing the star and getting the planet's radiation. So ultimately it is the same. But in this technique, what we are doing is we are not putting like a coronagraph. We are just measuring it as trying to go behind the star. Okay, but essentially, conceptually, the emission spectroscopy technique remains the same.
Yeah.
Okay.
Thank you, Professor.
Yeah. So I have just one last question I can see in the chat. I'll just answer that and then we can end. So Raghav is asking, why is photochemistry process in atmospheric important? So the photochemistry is important because actually, if you see the ozone that is forms in the Earth's atmosphere, that is because of photochemistry. So the photons, the UV photons coming from the sun are interacting with the oxygen in the Earth's atmosphere, making oxygen atoms that ultimately forms ozone. So that is the reason photochemistry plays a very important role in the atmosphere. And it can have many such photochemical processes can happen in the planetary atmosphere depending on its composition, the stellar spectral type, all that. So that is why this process is important. Okay.
Yeah, thank you, Dr. Jayesh, for answering all the questions, and it was really interesting session, and mostly like most of the, you posted, quiz questions, and most of the participant actually, it was really interactive. So you
you for
already
that.
shared, thank you so much for, having this session with us. And so participant, we'll have a next lecture tomorrow again. So see you tomorrow around 4:25. We'll start the session sharp by 4:30. Thank you so much. We are closing the session now. Thank you, Dr. Jayesh.
Thank you very much, everyone. Bye.
Thanks a lot. Bye.